So for CCENT Chapter 11, we're going to be talking about the transport layer. And the transport layer here is actually not that difficult. It's actually a pretty simple discussion. We're going to do kind of a high-level discussion of what happens at the transport layer. We know that the transport layer is layer 4 of our OSI model, right? It's layer 4 of our OSI model. We don't have any devices that function at this layer specifically. We certainly have devices that can read information at this layer because we know that we can do things like filtering on TCP and UDP port numbers. But for the most part, we only have 2 applications that function at this layer, TCP and UDP, 2 protocols, I should say, okay? Remember, we talked about this as, excuse me, as being the host-to-host layer, right? Why do we call it the host-to-host layer? Any ideas? Why do we call it the host-to-host layer? Because this is the first layer where only the hosts care about what's happening at this layer. Switches don't care about what happens at this layer. Routers don't care about what happens at this layer. So this is the first layer where we see host-to-host communication, okay? We know that there are 2 protocols that function at this layer. We also know that the transport layer is responsible for establishing communication sessions between endpoints, hosts specifically. And we have 2 protocols that function at this layer, TCP and UDP. TCP, as you can see from this particular slide here, TCP is a connection-oriented protocol. What does it mean for a protocol to be connection-oriented? Any ideas? What does it mean for a protocol to be connection-oriented? It means that we establish a dialogue or we establish a session with the destination prior to actually sending information. We'll see more about that in detail as we move through the chapter. Best effort and connection list for UDP. Sequencing for TCP. No sequencing for UDP. So as you can see, TCP is considered to be a reliable transport protocol, whereas UDP is considered to be best effort only. So you might consider, well, why would I ever want to use UDP? If UDP doesn't have any of that functionality built into it, what is the point of using that protocol? Well, frankly, the point of using the protocol is there are applications that exist that can't take advantage of those resources. For example, if you're having a real-time voice conversation, how can you delay the delivery of the segments or the datagrams while you're getting retransmissions? It would effectively mess up or degrade that audio call or that audio transmission. So most of our data applications that we use every day, email, web browsing, etc., that's all going to be pretty much based on TCP type applications, all right? Whereas video streaming, voice streaming, stuff like that, that's going to be, those are real-time applications. They're going to use UDP because UDP has less overhead. All right, we'll see what the overhead looks like as we start to go through the details of each of these protocols a little bit later on. We talked about the concept of MTU in one of our first lessons. We also talked about the concept of session multiplexing, right? You guys remember what multiplexing was? Taking lots of different conversations and interleaving those conversations across the wire. Here's a perfect example. I've got a computer that's running lots and lots and lots of different applications. But that computer only has one physical connection to the network. That computer only has one physical connection to the network. So all of those applications have to share that particular resource. What does that mean for us? That means that the green conversation, which is my voice over IP, the purple conversation, which is my instant messaging, we're going to divide those conversations up into multiple pieces. And as that data gets streamed out of the interface, we're going to interleave those conversations, pieces of information. So all of the applications get access to the network equally. You guys remember we talked about this concept in the form of segmentation and in the form of dividing the message up into multiple pieces, and specifically with something called an MTU. Now this is specific to this host, but this also happens from host to host to host. All right? What is the downside to dividing the data up into individual pieces? We talked about that on day one. The downside is that we're increasing the amount of overhead to transmit the data because every one of those squares now has to be individually encapsulated into an IP datagram, into a frame, and sent over the wire. But network communication would not work without that process. Now, different applications have different types of reliability needs. Most of my data applications are drop-in sensitive or delay-in sensitive, meaning they can handle a certain number of drops, they can handle a certain amount of delay. If your email takes an extra 40 milliseconds or an extra 100 milliseconds to reach its destination, you probably won't notice the difference. But if your audio packets for your voice conversation take an extra 100 milliseconds to reach its destination, you'll know. All right? So it's a little bit counterintuitive. The applications that are drop-in sensitive, the applications that are delay-in sensitive will use TCP, the Transmission Control Protocol. TCP has a bunch of mechanisms built into it to ensure delivery of our data, reordering or resequencing of our data information so that we can construct our conversations. UDP, no reliability functions, no guaranteed order of delivery, etc. There's a trade-off that you have between having that reliability and having the ability to retransmit or resend information to not. And that trade-off comes in the form of overhead and complex communication. So let's break down each of these protocols and do kind of a compare and contrast between the two. And then we'll wrap up the chapter by talking about different types of applications, layer 7 items that use these particular types of protocols. TCP, the Transmission Control Protocol, number one, connection-oriented, meaning that we establish a session between the source and the destination. And when I say source and destination, I'm talking about the sending host and the receiving host. I'm not talking about the routers in between. I'm not talking about the devices in between. This is a host-to-host layer. We have reliable delivery, meaning that if data gets lost or data doesn't make it to its destination, we can recover that information, resend just that piece of information to ensure that we have our entire payload. And we do this by using things like acknowledgements. We have sequence numbers that identify each of our segments in our data stream and allow us to control the delivery of that information. Okay? Flow control. Speeding up or slowing down transmissions based on how quickly or how slowly the device can process information. Think about it for a second. You're an individual host. If you're going to a web server to get information from a web server, you might not be the only device talking to that web server. Most likely you're not. So even though you may have a lot of resources available to process information and data, that web server might not. So the web server has to receive or send information at a slower speed than, say, for example, your individual host. This is what our TCP header looks like. At layer 2, we looked at a data link layer header. At layer 3, we looked at our IP headers. Now we get to see what our transport layer header looks like. The first two fields you see in your TCP header are the port numbers. We've been talking about port numbers throughout the class, kind of referencing these ideas of, oh, it's port 80, or it's an ephemeral port at 3192, whatever it might be. But these port numbers are to the transport layer like the protocol field is to the network layer, or the type field is to the data link layer. In other words, the port numbers allow us to identify the applications that we're using. Now, if you're talking about communicating from a host to a destination, typically that source port is going to be some sort of randomly generated ephemeral port, and the destination port is going to be some sort of well-known application port, like port 80 or port 22 or port 23 or whatnot. We'll talk more about port numbers as we move through the rest of the slides here. We have a sequence number, very, very important concept with TCP. That 32-bit sequence number allows me to identify that segment. Because when I'm sending multiple segments to my destination, it's possible that that segments might actually be displayed out of order. Maybe I lost a segment in between, so I'm going to have to retransmit that segment. So the sequence number allows me to identify the order of delivery. So for example, TCP segment 1, TCP segment 2, TCP segment 3, TCP segment 4. If 3 doesn't arrive at its destination, I can retransmit 3 at the end. But because I have these sequence numbers, the host at the receiving side can put the data back in order and send it to the application in the appropriate order that it came in. We have 32-bit acknowledgement numbers. 32-bit acknowledgement numbers. We'll talk about what an acknowledgement is, but in a nutshell, it is a way for the receiving host to send a message to the sending host saying, hey, I got the information, thank you. I'm acknowledging the receipt of information. We have some other fields here. We have a header link field. Now, what did I tell you guys about a header link field when we were talking about IP? When you have a header link field, what does that mean? That means that the header is variable in length. The header is variable in length. It might be 20 bytes, it might be 30 bytes, it might be 40 bytes. By the way, a TCP header is, in fact, by default, 20 bytes. Oops, I drew that line wrong. From here to here, it's 20 bytes. If you add options, it goes above 20 bytes. And of course, data is everything above layer 4. It's the payload. So this header link field will allow us to identify whether or not we're using a standard TCP header or whether or not we've implemented some sort of option in TCP to extend the length of the header. We have these flag fields. Here's a list of all the flags that exist. Now, we don't go into detail on each of these flags. We'll talk about a few of them, but things like synchronization flags, what we call the SYN flag, or the acknowledgement flag, ACK, or the FIN flag, to finish a conversation, or the urgent flag, congestion notification flag, and so on. These are individual bits in that field, and if you'll notice, there's 1, 2, 3, 4, 5, 6, 7, 8 of them. That makes sense. That's an 8-bit field. Those letters represent the flag. Obviously, those are not hexadecimal letters. They just represent the function, right? Congestion window reduced, CWR. Explicit congestion notification. urgent, ACK, push, reset, SYN, FIN. These flags are used to control the session. If certain transactions are taking place within TCP, we can identify those transactions by setting those individual flag bits. We have another 16-bit window called the 16-bit field called the window size. Window size is used for flow control to identify how much data can be sent before I expect to see an acknowledgement. We have some slides that describe that process a little bit later on as well. We have a checksum, right? What is a checksum? Checksum allows me to do what? We saw checksums at layer 2. We saw checksums at layer 3 to verify the integrity of the header. In the case of TCP, this checksum allows me to identify the integrity of the header plus some of my payload information. All right, you see it down here described. The checksum of the entire TCP segment and pseudo header, parts of the IP header, get verified. So those are the components of our TCP header. As you can see, there are a lot of components within TCP, but all of these components are there to provide reliability. What do you think UDP is going to look like? Well, let's talk a little bit about UDP. UDP doesn't have any of that reliability. No guaranteed delivery, no reordered construction, no flow control. It is a stateless protocol. So look at our UDP header as opposed to TCP. Our TCP header was 20 bytes. Our UDP header is only 8 bytes. In fact, the only 3 fields that are common are those: source and destination port and checksum. Remember I said all that reliability that we talked about with TCP, all of that results in overhead. The more overhead we have, the less efficient the protocol becomes. So we like to kind of have less overhead. All right. I'm going to pause the recording for a second here. Give me 1 second. All right. Sorry about the delay, guys. We're in the process of setting up the testing system. He's got to update the software and stuff like that. So trying to get everything set up. We brought our testing, our Pearson View testing center from Simi Valley over here so we can get you guys tested tomorrow. So anyway, UDP. UDP, as I mentioned before, is very low overhead. Now, what is the importance of port numbers? Well, this slide actually depicts that concept very clearly. I'm on a computer in the network. I open up a web browser and I connect to a web server in the same network. And this applies to whether the destination is in the same network or not. The top PDU describes that conversation. Look at the source MAC address. It's the PC, right? Destination MAC is the web server, the other way around, right? This is the PC, this is the web server. Well, in my second browser, if I open up a second web browser, those 2 pieces of information are going to be the same, aren't they? It's the same physical source, it's the same physical destination. You guys agree with that? In fact, even at the IP layer, it's the same source and same destination IP. Now imagine what we have. We have a computer with 2 web browser windows open. And I went to the same web server and opened up the web page. Even the destination TCP port is the same, because port 80 is a well-known port that we use for web traffic. Port 80 is a well-known port that we use for web traffic. Wow, okay. So when the web server is responding to the request, how does it know to send the data to application window number 1 or application window number 2? Well, this is where that source port comes into play. Every single time a host opens up a connection, whether it's TCP or UDP, whether it's web traffic, FTP traffic, whatever it is, the host generates its own random source port. That is the only thing that distinguishes the communication from one channel to the other, because everything else about this conversation is the same. So my first browser, I started with port 1305. My second browser, I started with port 1099. So when the web server is replying, it knows to send this data up to application window number 1 because it matches port 1035. It knows to send that data up to application window number 2 because it uses port 1099. That's how we distinguish between unique conversations. The server destination port is 80. The client source port is what varies. That client source port is called an ephemeral port, EPH something, ephemeral, whatever, however you spell ephemeral. All right. Okay. Now, it's not to say that we don't have other applications that use other ports. I mean, port 80 is used for web, port 22 is used for SSH, port 23 is used for telnet, and so on. So we have different types of applications that use different port numbers. All right. Speaking of those port numbers, we know that the port number field is 16 bits, right? The port number field is 16 bits. Did you run RMA, Mike? No. You have to run RMA. Did you already complete the registration? Yep. So you need to go back to the TeamViewer window. You're in the laptop. Go back to the TeamViewer window, and you need to run RMA. Click the Windows icon. Yeah. Okay? Remember, that field is 16 bits, which means we have a limited range of ports that we can have, 0 to 65,535, because 2 to the power of 16 is 16,536. Guess who manages these port numbers? The IANA, the Internet Assigned Numbers Authority. Now, in the first block, from 0 to 1023, we have what are called well-known ports. Well-known ports are registered ports for applications that we see on a regular basis. These are applications that we see every single day, like port 80 for web traffic, port 20 and 21 for FTP, port 23 for telnet, port 53 for DNS, and so on. These are the port numbers that you guys are going to be responsible for knowing for the exam. So you know that there's some that are TCP related, some that are UDP related, and even in some cases, you have a protocol that uses both TCP and UDP. DNS, the domain name service, uses both TCP and UDP. So the first thing we see is we have these well-known port numbers. The IANA is responsible for registering those well-known port numbers. Honestly, they really haven't changed that much. I mean, HTTP has been port 80 forever. Not forever, but, you know, in terms of networking time, yes, forever. Right? SSH has been port 22. Telnet has been port 23. FTP is actually both 20 and 21. We use different port numbers for that. Now we have another range here from 1024 up to 49,151. From 1024 to 49,151, these are called registered ports. These ports are used for other applications. Obviously, we have more than 1,023 applications that exist around the world. So companies will register their applications so that when you're setting up firewall rules or access rules or setting up security in the network, you can ensure that your application is supporting your security policies support the application by some sort of registered port. But the interesting thing about this range, and actually the entire remaining range, that's what's used for my source port as well. That ephemeral, there we go. That's my ephemeral range. So as a client, you can actually generate your traffic from any port from 1024 all the way up to 65,535. So it is possible. It is possible that you might see your host using a port that's registered to another application as a source port. Okay? That being said, if you're using Wireshark or whatnot to capture that information, it might be reporting in Wireshark that you're using that application, but it's actually not true. You just happen to be using that port number that that application was registered to. All right? If you want to see what types of applications you're running on your host, what types of TCP or UDP sessions that you have active, you can use a command line syntax and type in Netstat. Netstat will show us our active connections. It even shows us what ports we're listening on. This particular computer was listening on port 135, 445, 843, 5357, and so on. You might see that and go, well, what is port 135? What is port 445? We know that those are well-known ports, aren't they? Those are definitely well-known ports. They fall within that range, don't they? All right. But you can also see what types of connections you have established. You can see what types of connections that you have established to external destinations. Netstat is a good way for you to kind of identify if you have maybe a keylogger running on your computer, or there's some sort of back-end application that you're not aware of you know, that's running, and you might not be aware of it, right? So we can use this application or this command to identify that. Okay. Another part of the process within TCP and UDP is this concept of a three-way handshake. Give me a minute, Mike. I'll come over there and assist, okay? This three-way handshake, what we call the connection establishment process. You might want to move that over to maybe a different port. The camera, just move it to a different USB port. All right. What is the three-way handshake? It is a way for our devices to establish a communication channel with the destination prior to sending our information. Okay? Of course, we know that this only occurs in TCP. It does not occur in UDP. It only occurs in TCP. All right? What is the purpose of the three-way handshake? The purpose is to verify that the destination device is active, that the service that's supposed to be running is running. The service meaning, is it a web server? Is it running web services? Is it listening on port 80? And so on. Okay? It also informs the destination device that the source is intending to establish that session so that it can communicate. The first thing that has to happen when I want to talk to a web server is I'll try to establish a session with that web server. This is what that handshake looks like. We send a connection request in the form of a synchronization. It's called the SYN flag. The SYN flag. SYN flag gets set, meaning we're trying to synchronize with that destination. The server then responds with a SYN flag still set, saying, I understand that you're trying to establish a connection, but in addition, I'm going to go ahead and establish an acknowledgement, telling you I'm acknowledging that you're trying to establish a session. And then lastly, the client says, okay, great. I acknowledge your acknowledgement. Let's go ahead and start communicating. This is called the three-way handshake because it's a three-step process, 1, 2, 3. Once that process is done, then we can start actually sending and receiving data. Make sense? But only after that process is done can we start sending and receiving data. This is what that three-way handshake looks like in Wireshark. So let's break this down. If you look at the first, this is the original SYN. This is my SYN-ACK, and then this is my final ACK, okay? So if you look at the process here, the source port is 56.159. That's the ephemeral port, right? The destination port is 80, so I know that this is an HTTP connection request. The sequence number is 0 because this is the initial communication that occurs. Now, we'll talk about sequence numbers a little bit later in detail, but sequence numbers allow us to identify the order of segments as they're delivered. The header length is 32 bytes, which means that this particular TCP segment has options. In fact, it has 12 bytes of options. You can see it down here. We know that our standard TCP header is 20 bytes, but because this header is 32 bytes, I have options. We can see that the SYN flag is set. The SYN flag is set, meaning that we're performing asynchronization. All right? Sorry about that. So the second part of this conversation, if you look at the second capture, we see the port numbers, the port numbers actually changed, didn't they? We went, port 80 became the source, and port 56159 became the destination. Because this is the traffic coming back from the web server going to the client. Also notice that the acknowledgement is 1. The acknowledgement is 1, meaning I am acknowledging the original sequence number. By the way, we always acknowledge the next sequence we expect to receive. If you just sent me sequence 0, I'm going to acknowledge 1. If you send me sequence 50, I'm going to acknowledge 51. All right, we'll see a little bit more about that in a couple of slides here. There's another thing that's being negotiated here. I'm not going to point it out. I mean, I'll point it out right now, but we'll talk about what this is a little bit later on. It's this thing called a window size. That's another component of this TCP three-way handshake, negotiating this thing called a window size. Like I said, we'll talk about what that window size is in a little bit. Notice on the second segment, 2 flags are set, the SYN flag and the ACK flag, meaning that I'm acknowledging your request to synchronize with me or to set up, establish a session with me. What does this tell the client? It tells the client that port 80 is responding, because that acknowledgement came from port 80. It tells the client what kind of window size the server can use. And then finally, the final acknowledgement, the port numbers swap again. My acknowledgement number is 1, or sequence number is 1, because that's the next sequence you expected to receive. And we can see that the window size has changed again. Now, we're going to learn all about what that window size does here in a little bit. All right? We're going to learn all about what that window size does here in a little bit. But it's a very important concept within TCP. We don't have this function in UDP. In UDP, there is no concept of a three-way handshake. There aren't even any flag fields. No flag fields, no window size, no sequence numbers, no acknowledgement numbers, none of that stuff. Okay? The only thing we see in UDP are the port numbers. Additionally, with TCP, we have these graceful closes, right? Meaning that we're ending the session when we're done. I send you a TCP segment with the fin flag set. Fin stands for finish. Trying to end the conversation. You send me an acknowledgement. You send me another segment indicating that you're ready to close the session. I send you an acknowledgement, and through that process, we shut down our TCP session. Now, this doesn't always happen, right? I mean, what if I was to just shut off my computer right now? There wouldn't be an opportunity for me to close out these sessions, right? So oftentimes, sessions get closed out without going through this graceful process. Those are called zombie TCP sessions or zombie TCP connections. And those zombie TCP connections will eventually age out or will eventually time out. Okay? Mike, if it's a Logitech, that would be perfect.
Okay.
I don't know if another one will work or not, but.
Okay.
Okay? Of course, the other concept that we talked about with regard to TCP is the ability to do reordering of our segments. Of course, we know when data leaves the host, all of the segments are in order. I send you segment 1, I send you segment 2, I send you segment 3. But during transit, some segments might go this way, some segments might go that way, some segments might go that way. So segments might arrive out of order. Or I might lose segments in between, which means I have to recover those segments. If I lose segments in between. The bottom line is whatever shows up at the receiving side isn't in order. We've got segment 1, segment 2, segment 6, segment 5. So what does the receiving host do with this data? It stores or buffers that information until it can reorder that information and send it up to layer 7 as it was delivered originally. What do we use within the TCP header that provides this function? What do we use within the TCP header that provides this function? Sequencing. We use sequence numbers. Yes, sir.
So within the TCP header, it tells how many segments. So before it represents or project the whole message.
No. I mean, you would think that that might happen. The question was, in that initial negotiation, does the sending host tell the receiving host how many segments are coming? And actually, that's not the case. The only thing that the receiving host knows is that data is coming. But it doesn't know how much data the sender's actually wanting to send.
But it doesn't tell them in the header, in the TCP header?
Nope. There's nothing in the TCP header to indicate the number of sequences that are going to be sent, the number of segments. Okay? It might be 100 segments, it might be 1,000 segments, it might be 10,000 segments. We don't know. However, we do know how many segments are going to be sent before you need to send me an acknowledgement. That's a little bit different. That's something called the window size. Right?
For the sequence number, I know it's 32-bit.
Yes, 32 bits, yes.
So, like, is there ever, like, you know, if you're sending a huge file, will it ever...
No, and that's the reason why that sequence number is so large, because you don't want to have to use a duplicate sequence number. I mean, 32 bits, that's a large number.
Yeah, it's like
2 to the power of 32, right?
4.2 billion.
Yeah, you're not going to send 4.2 billion segments in one conversation. You have to remember, this is just one transaction, me opening up a web page or me sending an email. It's not the whole time. Every new TCP connection has its own range of sequence numbers. All right, we have a question here. The number can change anyway because the receiving unit can slow it down or send smaller packages, correct? Yes, that's true. The window size, he's referring to the window size, that window size can change. And we'll have a slide to discuss what the window size is all about. But let me be clear that you open up a FTP session to a server. That is a separate communication channel. The sequence numbers in that FTP session are completely irrelevant from another channel where you're doing web browsing. It's only during that session that those sequence numbers matter.
Yeah, okay. No, I was just considering, for larger files that
Right. Think about what's going into a segment, okay? What's going into a segment is a payload. And if it's Ethernet, it's 1,500 bytes of data. Now multiply that times the number you came up with. That's how much data you would have to send in one session for that sequence number to be oversubscribed. 1,500 bytes times 4 billion different sequence numbers, right?
Yeah.
That's bytes. Now, our packages, of course, include, we don't use a separate sequence number for each byte. I mean, I guess technically we do, because if I send you 10 bytes of data, the sequence number is 10, you're going to acknowledge 11, meaning that you received the first 10 bytes of data, now you want to receive 11 forward. I send you another 10 bytes of data, the sequence number is 20, which means you're going to acknowledge 21. So mathematically, it works out that the sequence number would have to correspond to the field size. In order to exceed that, we'd have to send that many bytes. But that typically wouldn't happen. Actually, probably would never happen, honestly. So we've been talking about this concept of window size. What does window size represent? In TCP, we send acknowledgments. We acknowledge the receipt of information. Now, I don't acknowledge every single byte you send. If I sent an acknowledgement for every byte of data that you sent me, we'd have so much overhead just for providing acknowledgments, right? So what the window size does is it allows us to establish how many bytes of data can be sent before I expect to receive an acknowledgement. Here's an example. I have a window size of 3,000. Now that doesn't mean that I can put 3,000 bytes of data into one segment, but it means that I can send X number of segments up to that window size. In this particular case, segment 1 and segment 2. So my initial sequence number is 1, because that would be what it would be after my three-way handshake. I send you 1,500 bytes of data. Now, if my window size was 1,500, at that point, you'd send me an acknowledgement. But because the initial window size that was negotiated is 3,000, I send you segment 1, I send you segment 2. At that point, you acknowledge 3001, telling the receiving host, telling the sending host, I received up to 3,000. I received the information up to 3,000. Now I send you segment number 3, segment number 4, which takes me up to 6,000 bytes, and you acknowledge 6,001. So the window size determines the number of bytes that can be sent before an acknowledgement needs to be received. The larger the window size, the less overhead, right? The larger the window size, the less overhead. The smaller the window size, the more overhead. Now, in TCP, we use something called the sliding window. In TCP, we use something called the sliding window. What does that mean? What do you think it means to say a sliding window? It means that the window size adjusts. What do you think would cause the window size to go down if you lose a segment? What do you think causes the window size to go up? The reliability of the connection. The more reliable the connection between the clients, the larger the window size. There are other things that can affect the window size as well. For example, you being a client, you don't have thousands of people trying to access your information. But the web server has thousands of people trying to access its information. So the web server can handle less information than the sending client can. That's why we saw in this, example here, the initial window size value was set to 65,535, which happens to be the max based on a 16-bit field. The server responded and said, my window size is 14,800 bytes or 600 bytes. So the server says, if I send you 14,600 bytes of data, you need to send me an acknowledgement. The client says, if I send you 65,535 bytes of data, you need to send me an acknowledgement. And then the client readjusted the window size. It looks like it went down, but actually we're using a scaling factor, 8 times 32,768, which gave us a window size of 262,144. The larger the window size, the more efficient the communication. Here we had an initial window size of 3,000. I sent segment 1, segment 2. You acknowledge 3001. Great. You acknowledge the next segment you expect to receive, which means I know that you received the first 2 segments. I send you 3001 and 4501. I expect you to acknowledge 6,000, but you don't. You acknowledge 3001. And on top of that, you set or adjusted the window size to 1,500. That tells me 2 things. That tells me, number 1, you dropped or sequence number 3 was lost, but you did receive sequence number 4 because the window size was only adjusted by half. So I resend you 3001, then you acknowledge 6001, which means I can now go on to sequence number 6, or 5, excuse me, and then 6, and then 7.
So with the receiver acknowledging 6001, that's also him acknowledging that he before.
That's right. That's because why resend everything?
Yeah.
Why not just send the piece that I lost, right?
Yeah.
And that's what's happening here. So that's what we're talking about, this buffering and this reordering function. We're storing this information. Now, I have to say, and I do this every class, this is a very simplified explanation of this concept. In TCP, it's actually much more complicated than that. There are algorithms that are run, there are calculations that are done to set these values. The values we're using on this slide do not really represent a true TCP session. So when you look at Wireshark, it's not going to be nearly as concise as what you're seeing here. But fundamentally, the concept is the same.
With essentially with the acknowledgement number, that would just equal the amount of bytes that I did.
Yes, the acknowledgement number, well, the sequence number is usually tied directly to the amount of bytes that are being sent. The acknowledgement number generally represents the next byte you expect to receive. So if I send you 3,000, I expect you to acknowledge 3001. If I send you up to 6,000, I expect you to acknowledge 6001 and so on. That make sense? Okay. We know that UDP doesn't do any of this. So UDP has very low overhead. But the trade-off is you lose all of the reliability. All right, there are some applications like Domain Name Service, Simple Network Management Protocol, DHCP, the Trivial File Transfer Protocol, Voice over IP, specifically RTP. These all use UDP. Some of them are real-time. Some of them are more like data applications. Understand that just because the reliability is not built into UDP doesn't mean that the application is unreliable. In some applications, the reliability functions come at a higher layer. In other words, whoever wrote the application decided to put the reliability into the application rather than relying on a lower layer to perform that function. So SNMP has some reliability functions built into it. just not at the transport layer, at the application layer, okay? Unfortunately, when it comes to UDP, if data gets received out of order, within UDP, there's no way to do reordering because we don't have sequence numbers. Again, that does not mean that the data gets sent to the application out of order. There may be a sequencing component at another layer providing that functionality. RTP, for example, which is used for voice over IP, RTP has a sequencing function built into it. All right. Last couple of slides here, and then we'll take our afternoon break. We've got some TCP applications, some well-known ones, HTTP, FTP, SMTP. SMTP is used for mail transfers, right? Simple mail transfer protocol. Telnet, we know what Telnet is. DNS, domain name service. These are some common TCP applications. In UDP, we see some more TFTP, SNMP. DHCP is interesting. We'll talk about DHCP a little bit more, the Dynamic Host Configuration Protocol. It actually uses a subset of protocols called BootP, BootPC and BootPS, which is our boot protocols. All right? All right, so that wraps up that chapter. Sorry about the breaks in between. We're trying to get things set up here, but we'll move on to the next chapter here in a few minutes. Rather than kind of stopping and starting, let's go ahead and take our break now. We usually do a break at 2:30 anyway. Hopefully I can get everything ready.